Hello, my name is Sean Kenny. I go to the Chesapeake Bay Governor School Bowling Green campus, and this is my presentation on the effects of urban development and riparian buffers on an urban stream. So the idea for my project came about one day when I was walking along a trail in Fredericksburg, Virginia, and I noticed that the stream that followed the trail looked like it was really muddy and a little dirty. And so I wanted to investigate whether the area around the stream, which was mainly urban development, was having an effect on its water quality, and I also wanted to test if the riparian buffers around the stream were effective at protecting its water quality. So I'll start off with some background on urban water quality impacts and riparian buffers. Then I will go into my testing location and my study sites. I'll state my hypotheses. I'll follow that with some discussion on my variables and the water quality testing methods I followed. And I'll wrap up with some results and conclusions, including what my data suggests about riparian buffers in urban areas and whether rainfall could have impacted my study. So the most common cause of water quality issues in urban areas is non-point source pollution, which is just polluted runoff. And in urban areas, it's worsened due to impervious surfaces like sidewalks and roadways that don't let water soak into the soil. Urban areas and construction areas can have many impacts on water quality, including increased turbidity, phosphate and nitrate pollution, increased temperature, and increased pH. So riparian buffers are areas of vegetation that border bodies of water, and they protect stream water quality and aquatic life by acting as a physical barrier to polluted runoff. And by acting as a physical barrier, they're able to collect excess sediments, nitrates, phosphates, and prevent those from entering the water and negatively impacting water quality. They also maintain stream temperatures, which is important for certain aquatic organisms. So there's been a lot of previous research on agricultural and rural environment where riparian buffers have been used, but not a lot on urban riparian buffers. So my study wanted to investigate that aspect of them. The location of my study was the Hazel Run Stream in Fredericksburg, Virginia. I had two sites, Site A and Site B. On this map, the stream flows from left to right towards the Rappahannock River on this side. Site A is upstream from Site B, and it was surrounded by much more riparian vegetation than Site B, which only had a riparian buffer on one side. And so I wanted to see if the urban area around both sites was having an impact on their water quality. An area of heavy residential construction that was relevant to my study is outlined here, and I was interested in seeing if that was having an impact on Site B and not Site A. I included this map here on the right to highlight the fact that the stream is impacted by a much larger watershed than what is shown in this map, and that watershed is characterized by other urban areas that have impervious surfaces and fertilized lawns and construction, and as well as some other forests. Site A was my upstream site. It was shallow and rocky, and it was surrounded by a large, dense old-growth woodland forest on all sides. Site B was also shallow and rocky, but it only had a forested riparian buffer on one side, and on the side shown on this video, you can see that it had a much narrower riparian area of riparian vegetation that was younger and much less established. And it was also downstream from construction and a lot of urban development. There was a large construction site close to the stream that was upstream from Site B and downstream from Site A. It was a large area of housing construction and already constructed homes. It had some fertilized lawns, and there were some stormwater management methods in place to prevent it from having an impact on the stream, like silt fencing, rock bags, culverts, and drainage reservoirs. On the left-hand side of the video right now is about where Site A is, and on the right-hand side is about where Site B is. So they were very close, but Site B was still downstream from this area of construction. So my null hypothesis is that the water quality at both sites would be equal to each other, and my alternative hypothesis was that the water quality at Site A would be better than the water quality at Site B because Site A had a much larger riparian buffer and it was farther away from urban development, while Site B was quite the opposite. The independent variable of my study was the location of testing sites, which was chosen based on the riparian vegetation it had and the proximity to urban development. The dependent variables of my study were the turbidity, temperature, phosphate and nitrate concentrations, pH, and dissolved oxygen of the stream at both sites. And my monitoring variables were ambient air temperature and flow rate, and my controls were the testing equipment I used the procedure I followed, and the specific part of the stream that I tested at. I collected data 7 times from August 28th to October 22nd, 2021, and one of the most helpful resources I used was a multi-parameter aquatrol sonde, which was a probe that I would lower into the water and it would send data on temperature, pH, and dissolved oxygen to an iPad. Another helpful instrument I used was the transparency tube, which I used to measure my dependent variable of turbidity. I also used a flow probe, which helped me get my moderating variable of flow rate, and then also to get my last dependent variables of phosphate and nitrates, I used lab testing kits, vacuum vials, and a spectrophotometer to measure their parts per million. So this is a table of my results. This is the average water quality of my different variables at both sites, and at quick glance you can see that the results are very similar at both site A and site B. And this is supported by the fact that the p-value of each variable is very high, indicating that there's no real significant difference between the water quality at both sites. Here's my first graph of dissolved oxygen. The y-axis shows dissolved oxygen, and the x-axis shows both sites. These values actually turned out to be the exact same, and the p-value of 0.99 indicates that these results are statistically not different. This is my second graph of water temperature. The y-axis shows the average water temperature in Celsius, and the x-axis shows both sites. These values were slightly different, but the p-value of 0.74 still indicates that the water temperature at both sites was not statistically different at all. My third graph shows a similar story. This is pH at both sites. The y-axis shows the pH scale, and the x-axis shows both sites once again. These values were also very similar and had a high p-value of 0.9, indicating the results were not statistically significant. This is my last graph of turbidity. The y-axis shows turbidity in centimeters of visibility, which I obtained from the transparency tube. And site A and site B are on the x-axis. These values were slightly more different than the other results, but the p-value of 0.87 indicates that these are also not statistically significant. So since my results were not statistically significant, I failed to reject my null hypothesis, and I can reject my alternative hypothesis. And despite obtaining unexpected results, the stream is healthy at both sites according to standards set by Virginia law. This indicates that the urban areas and the construction site near the stream are not having a significant impact on the water quality of the stream. And this could be due to some stormwater management practices that were utilized at the construction site, like fertilizers not being applied during round rain events, erosion and sediment control plans, and drainage basins and silt fencing. I'd like to clarify that these interpretations are relevant to the stream under relatively dry conditions, and I specify this because there was not very much rainfall during my study. So during my study, there was a lack of rainfall during the times I tested, and the reason that this is significant is because rainfall allows for increased runoff, and it is essentially how pollution enters streams in the first place and negatively impacts water quality. And especially in urban areas, during rain events, runoff bypasses riparian buffers via storm drains and culverts that drain water directly towards the stream. So I think a future study, if I were to do this again, I would really try to hone in on testing before and after rain events to see if there's a significant difference. And I would also try to see if maybe the riparian buffers have more of an impact during rain. So some key takeaways: the water quality of both sites was nearly identical despite having differing riparian buffer sizes and proximities to urban development, and this demonstrates a strong suit of my results because I had an adequate sample size and very high p-values. The results can generally be trusted to be representative of the water quality in the stream during relatively dry conditions. My study further highlights the importance of maintaining riparian buffers, especially in urban and suburban areas. Also, the stormwater management practices at the construction site could be considered to be effective, and I think a future study could investigate the effects of rainfall because my study was limited in that I was not able to collect data during significant rain events. Last but not least, I'd like to thank Dr. Goff for helping every step of the way, Dr. Ross for helping me plan my entire project last year, Ms. Wen for helping set up the aquatrol probe, and my parents and peers for support throughout this whole process. Thank you.